The edge of the universe is not a wall, not a boundary, not even a place one could travel toward. It is simply where space itself has not yet stretched into being. This is a strange thing to hold in the mind. The idea that expansion does not mean filling a room, because there is no room, no container waiting to be occupied. The cosmos unfolds into what we might call nothing, though even that word fails us, carrying as it does the suggestion of emptiness, when what we mean is the absence of existence itself. If these quiet explorations bring rest to your evenings, a subscription ensures more will find their way to you. For now, let the breath slow. Let the thoughts settle like dust in still air, and let this begin. For most of human history, the universe was understood to be a still and unchanging thing, a vast enclosure of stars and darkness that had always existed and would continue to exist in precisely the same arrangement for all of eternity. This was not merely a belief held by common people gazing upward from their fields and villages, but a principle endorsed by the greatest minds of antiquity, a framework so deeply embedded in philosophical thought that it persisted almost unchallenged for more than 2,000 years. The cosmos, it was assumed, simply was. It did not grow or shrink. It did not move in any grand sense. It hung, suspended in its own permanence, like a painting that had never been wet and would never fade. And humanity existed within it as one might exist within a very old house. A house that had stood since before memory and gave no indication of ever falling. Aristotle, writing in the 4th century before the Common Era, articulated this vision with particular clarity and authority. In his conception, the earth sat motionless at the center of all things, surrounded by concentric crystalline spheres that carried the moon, the sun, the planets, and finally the fixed stars. Beyond the outermost sphere, there was nothing at all, not empty space, not darkness, simply nothing, for the universe contained within itself everything that existed. This cosmos was finite but unbounded in the sense that there was no outside to speak of, no beyond to wonder about. The heavens were made of a perfect and incorruptible substance called ether, distinct from the earthly elements of fire, air, water, and earth, and this celestial material did not decay or change. The stars wheeled overhead in their nightly rotation, but this was circular motion, eternal and repetitive, a kind of motion that Aristotle considered natural to perfect things. It was change without alteration, movement without progress, and the universe as a whole remained fundamentally the same from one age to the next. This Aristotelian cosmos was remarkably durable. It survived the fall of empires and the rise of new religions. It was adopted and adapted by medieval scholars who found ways to reconcile it with their theologies, placing heaven beyond the sphere of fixed stars, but leaving the essential architecture intact. When Copernicus proposed that the Earth moved around the Sun rather than the reverse, and when Kepler and Galileo refined this understanding with mathematics and telescopic observation, the static nature of the universe itself was not seriously questioned. The Earth had been displaced from the center, certainly, and the crystalline spheres had been abandoned, but the stars remained fixed in their positions relative to one another, scattered perhaps through a vast space rather than embedded in a single sphere. yet still and eternal nonetheless. The revolution in astronomy that unfolded between the 16th and 18th centuries was a revolution concerning the arrangement of the solar system, not the behavior of the cosmos at large. Isaac Newton, whose laws of motion and universal gravitation transformed our understanding of physical reality, also inherited this assumption of cosmic stillness. In his system, every object with mass attracted every other object with mass, and this gravitational pull extended across the entirety of space, diminishing with distance but never vanishing entirely. Newton himself recognized a peculiarity in this framework, a troubling instability that arose when one considered what should happen to a universe filled with matter. If every star attracted every other star, then why did they not all fall together into a single great mass at the center of everything? Newton's solution was to propose that the universe must be infinite in extent and roughly uniform in its distribution of stars, so that each star was pulled equally in all directions and therefore remained in place. This was a delicate balance, an equilibrium that required a certain faith in the steadiness of cosmic arrangements, but it preserved the essential idea that the universe was not going anywhere. It was simply there, vast and silent and unchanging, a stage upon which the drama of planetary motion and earthly life could unfold without the stage itself ever shifting. This conception of a static universe persisted into the 20th century, carried forward not by ignorance, but by the sheer weight of tradition and by the absence of any compelling evidence to the contrary. When Albert Einstein developed his general theory of relativity between 1907 and 1915, he created a mathematical framework of extraordinary power and elegance, a set of field equations that described how matter and energy curved the fabric of space-time, and how this curvature, in turn, dictated the motion of objects through it. Gravity, in this new understanding, was not a force acting at a distance, but a manifestation of geometry, the bending of space and time themselves. It was a profound reconceptualization, and when Einstein applied his equations to the universe as a whole, he discovered something unexpected and, to him, unwelcome. The equations did not permit a static universe. Or rather, they did not naturally permit one. When Einstein examined solutions that might describe a cosmos filled uniformly with matter, he found that such a universe would either be expanding or contracting. The geometry of space-time, according to his own mathematics, was dynamic. It wanted to move. This was deeply troubling to Einstein, who shared with his predecessors and his contemporaries the conviction that the universe must be eternal and unchanging. He could not accept that the cosmos might be growing or shrinking, that space itself might be stretching or collapsing. It seemed absurd, or at least philosophically unsatisfying. And so in 1917, he introduced an additional term into his field equations, a term he called the cosmological constant and represented with the Greek letter lambda. This cosmological constant was, in essence, a kind of repulsive force that could counteract the attractive pull of gravity on the largest scales. By carefully adjusting its value, Einstein could balance the inward pull of matter against this outward pressure and produce a static solution, a universe that neither expanded nor contracted, but simply sat in equilibrium, unchanging through time. It was an elegant mathematical fix, though it required a certain fine-tuning, a precise balance between opposing tendencies. Einstein published this model, satisfied for the moment that he had rescued the universe from the indignity of motion, and the cosmological constant took its place in the equations of general relativity like a small weight added to a scale. Many years later, after observational evidence had thoroughly overturned the notion of a static cosmos, Einstein reportedly referred to the introduction of this constant as his greatest blunder. The phrase has become famous, though the exact circumstances of his using it are somewhat uncertain, passed down through the recollections of colleagues rather than recorded in his own writings. What is clear is that Einstein came to regret his reluctance to follow his equations where they led, his unwillingness to accept what the mathematics was telling him. The universe, as it turned out, was indeed dynamic. It was expanding, and had been expanding for billions of years. And the cosmological constant had been an unnecessary correction introduced to preserve an assumption that was simply wrong. There is something quietly humbling in this episode. A reminder that even the greatest minds are shaped by the expectations of their era, that the invisible assumptions of a culture can constrain even revolutionary thought. While Einstein wrestled with his equations in Europe, astronomers in the United States were engaged in patient and painstaking observations that would ultimately provide the evidence he had been unwilling to anticipate. High in the San Gabriel Mountains of Southern California, above the haze and lights of the growing city of Los Angeles, the Mount Wilson Observatory had been established in the early years of the 20th century under the direction of George Ellery Hale. The observatory was home to what was then the largest telescope in the world, the 60-inch Hooker reflector, which had seen first light in 1908 and had since been joined by an even larger instrument, the 100-inch Hooker telescope, completed in 1917. These were remarkable machines, their great mirrors gathering the faint light of distant objects and bringing into view details that had previously been beyond human perception. On the quiet nights when the seeing was good and the air above the mountain was still, astronomers at Mount Wilson would spend long hours at the eyepiece or, increasingly, with photographic plates exposed for hours to capture light too faint for the eye alone. They observed stars and clusters. They studied the spectra of distant suns to determine their composition and motion, and they turned their attention to a particular class of objects that had long puzzled observers. These were the spiral nebulae, faint patches of light with distinctive pinwheel shapes that could be found scattered across the sky. Through smaller telescopes, they appeared as smudges, indistinct and mysterious, and there was considerable debate about what they actually were. The prevailing view at the time held that these spiral nebulae were clouds of gas within our own Milky Way galaxy, perhaps regions where new stars were forming or the remnants of older stellar processes. The Milky Way itself was understood to be vast, a great disk of stars spanning tens of thousands of light years, and it was assumed by many astronomers that this disk constituted the entirety of the universe. There might be empty space beyond it, dark and formless, but all the stars and all the matter that existed were thought to be contained within this single great system. The spiral nebulae, in this view, were local phenomena, relatively nearby objects embedded within the larger structure of our galaxy. Not everyone agreed. However, some astronomers suspected that the spiral nebulae were far more distant than this, that they were in fact independent systems of stars, separate galaxies comparable in size and complexity to our own Milky Way. This idea was not new. The philosopher Immanuel Kant had speculated about island universes in the 18th century, imagining a cosmos populated by countless stellar systems scattered through infinite space. But speculation and evidence are different things, and the observational data available in the early 20th century was ambiguous enough to support either interpretation. This ambiguity came to a head in April of 1920, when the Smithsonian Institution hosted what has since become known as the Great Debate, a public discussion between two prominent astronomers, Harlow Shapley and Heber Curtis. The event was held at the Smithsonian's National Museum of Natural History in Washington, and though it was framed as a scholarly presentation rather than a confrontation, the two men represented fundamentally different views of the scale and structure of the universe. Shapley, who had recently completed important work on the distances to globular clusters, argued that the Milky Way was enormous, far larger than previous estimates had suggested, and that it encompassed essentially all of observable matter. The spiral nebulae, he maintained, were relatively small and nearby, objects within our own galaxy rather than distant island universes. Curtis, by contrast, argued that the Milky Way was more modest in size and that the spiral nebulae were indeed external galaxies, vast and remote, separated from us by distances far greater than any star within our own system. He pointed to certain observations that seemed to support this view, including the presence of dark lanes in some spirals that resembled the dust clouds seen in our own galaxy, and the occasional appearance of novae in these nebulae that suggested stellar populations within them. The debate did not produce a clear resolution on the evening it was held. Both men presented their arguments carefully and with appropriate scholarly caution, and the question remained open for several more years. But the event captured something important about the moment. A community of scientists standing at the edge of a vast expansion in human knowledge, not yet certain whether the universe was a single island of stars or a sea filled with countless such islands stretching beyond imagination. What is perhaps most striking, looking back from our present understanding, is the comfort that the static and bounded conception of the cosmos provided. To believe that the universe was finite, unchanging, and fully accounted for was to believe that humanity occupied a comprehensible place within a stable structure. The stars might be vast in number and the distances between them unimaginably large, but there was a completeness to the picture, a sense that everything that existed was catalogued and contained. The night sky was a dome, or perhaps a distant sphere, and beyond it lay nothing at all, not even empty space, simply the absence of existence. This was not a frightening notion for most people who considered it. It was reassuring. It was the architecture of a universe that knew its place and kept it. The astronomers who climbed the mountain road to Mount Wilson in those years before the great discoveries, who spent their nights in the cold dark of the dome with the great telescope turning slowly to track the stars, were working within this framework even as they gathered the data that would eventually overthrow it. They did not know yet that the spiral nebulae were galaxies. that each one contained hundreds of billions of stars, that the distances to them were measured in millions of light years. They did not know that the universe was expanding, that space itself was stretching, that the calm and stillness of the cosmos was an illusion born of limited perspective and ancient assumptions. They simply observed, recorded, measured, accumulated the evidence that would soon transform everything. And in that quiet interval, in those few years before the old certainties crumbled, humanity rested within a universe that seemed as permanent as a house that had always stood, a dwelling place built by the slow accretion of philosophical tradition and scientific observation, steady and reassuring, and, as it turned out, on the verge of being swept away by the very act of careful looking that had seemed to confirm it. In the early years of the 20th century, in a small observatory perched on a hill in northern Arizona, a patient man began the work that would eventually whisper to us the first hints of a universe in motion. His name was Vesto Melvin Slipher, and he worked at the Lowell Observatory in Flagstaff, a facility originally established to study Mars and search for evidence of canals on its surface, a pursuit that had captured the imagination of the observatory's founder, Percival Lowell. But Slipher's attention drifted elsewhere, toward those faint smudges of light that astronomers of the era called spiral nebulae, objects whose nature remained deeply uncertain, and whose secrets would require extraordinary patience to coax into the open. The instrument Slipher used was a 24-inch refracting telescope, a beautiful piece of optical craftsmanship that gathered light through a large glass lens rather than a mirror, bending that light to a focus where it could be examined and recorded. Attached to this telescope was a spectrograph, a device that spread incoming light into its constituent wavelengths, much as a prism transforms a beam of sunlight into a gentle rainbow. By studying this spread of colors, this spectrum, astronomers could learn remarkable things about distant objects, including their chemical composition, their temperature, and, crucially, whether they were moving towards us or away from us. This last piece of information came from a phenomenon known as the Doppler shift, the same effect that causes the pitch of a passing ambulance siren to change as it approaches and then recedes, only applied to light instead of sound. When a source of light moves toward an observer, its wavelengths become compressed slightly, shifting toward the blue end of the spectrum. When it moves away, the wavelengths stretch out, shifting toward the red. By measuring the precise positions of known spectral lines, those characteristic fingerprints left by elements like hydrogen and calcium, and comparing them to where those lines would appear in a stationary source, an astronomer could calculate how fast the object was moving and in which direction. The concept was elegant, but the practice was extraordinarily demanding, particularly when applied to objects as faint as the spiral nebulae. Slipher began this work in earnest around 1912, turning his spectrograph toward the Andromeda Nebula, the brightest and largest of the spirals visible from the northern hemisphere. Even with his capable instrument and clear Arizona skies, the light from Andromeda was so feeble, so diffuse, that capturing a usable spectrum required exposure times that would seem almost unimaginable today. The photographic plates of that era were far less sensitive than modern detectors, and gathering enough photons to record a meaningful spectrum sometimes demanded exposures stretching across multiple nights. The telescope carefully tracking its target as the Earth rotated. The shutter remaining open for 20 hours, 40 hours, sometimes as many as 80 hours spread across several observing sessions. During these long exposures, Slipher had to ensure that nothing disturbed the delicate alignment, that clouds did not drift across the field of view for too long, that the clockwork mechanism driving the telescope kept perfect pace with the stars. It was meticulous, exhausting work, the kind of labor that required not brilliance in the dramatic sense, but rather a quiet, relentless dedication to precision. The first results were surprising. The spectrum of the Andromeda Nebula, when Slipher finally obtained it with sufficient quality, showed a blue shift, indicating that this object was moving toward the Milky Way at a remarkable velocity, roughly 300 kilometers per second. This was far faster than any star that had been measured, a velocity so extreme that it gave Slipher pause. But rather than retreating from the strangeness of this result, he pressed forward, turning his spectrograph toward other spiral nebulae, one after another, accumulating data with the steady patience of someone who understood that the universe would reveal its secrets only to those willing to wait. As the years passed and Slipher gathered more spectra, a peculiar pattern began to emerge. While the Andromeda Nebula and one or two others showed blue shifts, the vast majority of the spirals displayed red shifts, indicating that they were moving away from us. By 1917, Slipher had measured the velocities of approximately 25 spiral nebulae, and of these, 21 were receding. The speeds involved were astonishing, some of them exceeding 1,000 kilometers per second, velocities that dwarfed anything observed within our own stellar neighborhood. The data suggested something profound, that most of these mysterious objects were fleeing from us, and doing so with considerable haste. But what this meant in the larger scheme of cosmic structure remained unclear. In 1914, Slipher presented some of his early findings at a meeting of the American Astronomical Society, held that year in Evanston, Illinois. He stood before his colleagues and described, in his careful and unassuming manner, the velocities he had measured, the extreme redshifts that seemed to characterize the spiral nebulae as a population. When he finished speaking, something unusual happened, something that speaks to the quality of his work and the impact it made on those who heard it. The assembled astronomers rose to their feet and applauded, a standing ovation, a gesture of respect and recognition that was, and remains, quite rare in scientific gatherings, where decorum tends toward the reserved and where even significant results are typically received with polite nods rather than outward enthusiasm. The astronomers in that room sensed, perhaps without fully understanding why, that Slipher had touched upon something fundamental. And yet, despite this reception, the full implications of Slipher's measurements would take time to crystallize. The nature of the spiral nebulae themselves remained a matter of debate throughout the 1910s and into the 1920s. Were they relatively small objects within our own Milky Way, perhaps swirling clouds of gas and young stars? Or were they vast systems in their own right, separate galaxies comparable to our own, lying at enormous distances beyond the boundaries of our stellar home? This was the question at the heart of the so-called Great Debate, and until it was resolved, The meaning of those redshifts would remain tantalizingly ambiguous. In another part of the world, in Belgium, a young man was pursuing a path that wove together two callings that might seem, at first glance, difficult to reconcile. Georges Lemaitre was born in Charleroi in 1894, and from an early age he displayed both a deep religious devotion and a keen aptitude for mathematics and physics. He served as an artillery officer during the First World War, an experience that marked him as it marked so many of his generation, and afterward he entered the seminary, eventually being ordained as a Catholic priest in 1923. But Lemaitre's spiritual vocation did not diminish his scientific curiosity, and he pursued advanced studies in physics and astronomy with the same dedication he brought to his religious duties. Lemaitre studied at Cambridge under the guidance of Arthur Eddington, one of the most eminent astrophysicists of the era, and he also spent time at Harvard and the Massachusetts Institute of Technology, absorbing the latest developments in cosmology and familiarizing himself with the growing body of observational data on the spiral nebulae and their puzzling redshifts. He was well versed in Einstein's general theory of relativity, that revolutionary framework published in 1915 that described gravity not as a force acting at a distance, but as the curvature of space-time itself, shaped by the presence of mass and energy. Lemaitre recognized that Einstein's equations, when applied to the universe as a whole, seemed to have something important to say about its overall behavior, its structure, its fate. Einstein himself had grappled with these cosmological implications and had been troubled by what his equations seemed to suggest. Without modification, they implied a universe that could not remain static, that must either expand or contract over time. This was deeply counterintuitive to Einstein, who, like most thinkers of his era, imagined the universe as eternal and unchanging on the largest scales, a grand and stable backdrop against which the drama of stars and planets played out. To preserve this vision of cosmic stillness, Einstein introduced an additional term into his equations, a cosmological constant that acted as a kind of repulsive force, perfectly balanced against gravitational attraction, holding the universe in a delicate and eternal equilibrium. Lemaitre approached these same equations with fewer preconceptions. Working through the mathematics with care, he arrived at a different conclusion. In a paper published in 1927, Lemaitre described a model in which the universe was not static but expanding, with the distances between galaxies increasing over time. He derived a relationship between the distance of a galaxy and its velocity of recession, finding that more distant galaxies should be moving away more quickly, a proportionality that reflected the stretching of space itself. He even estimated the rate of this expansion, a value that would later become known as the Hubble constant, though it was Lemaitre who first calculated it. 2 years before Edwin Hubble published his own more famous work on the subject. Lemaitre's paper appeared in a journal called the Annales de la Société Scientifique de Bruxelles, a respectable but relatively obscure publication with limited international circulation. The article was written in French, which further restricted its readership among English-speaking astronomers. As a result, this remarkable work, which anticipated so much of what would later be celebrated as Hubble's discovery, went largely unnoticed by the broader scientific community. Lemaitre was a modest man, not inclined to self-promotion, and he did not vigorously campaign to draw attention to his findings. The paper sat quietly in the archives, its insights waiting to be rediscovered. Meanwhile, the strange data continued to accumulate. Other astronomers, building on Slipher's pioneering work, measured additional redshifts, and the pattern held firm. The spiral nebulae, now increasingly recognized as external galaxies far beyond the Milky Way, were overwhelmingly moving away from us, and the faster ones tended to be the fainter ones, which presumably meant they were also the more distant ones. This was not yet a fully articulated theory, not yet a clear vision of cosmic expansion, but rather a growing pile of observations, like unanswered letters accumulating on a desk, each one adding to a sense that something important was being said. If only someone could piece together the message. The redshifts were real. The velocities were immense. The objects in question were scattered across the sky in all directions, and in nearly every direction, they were receding. It was as though the universe itself was exhaling, as though some vast and silent process was carrying everything apart from everything else, stretching the fabric of existence in a manner that defied easy comprehension. But in the early 1920s, this understanding had not yet fully dawned. The evidence was there, waiting patiently, like seeds beneath winter soil, for the warmth of recognition that would eventually allow it to bloom into one of the most profound realizations in the history of human thought. Slipher continued his work in Flagstaff, adding more measurements to his catalogue, refining his techniques, publishing his results in the steady and unassuming manner that characterized his entire career. Lemaitre returned to Belgium, took up a professorship at the Catholic University of Louvain, and continued to develop his cosmological ideas, gently suggesting to anyone who would listen that the universe had a history, that it had perhaps begun in some unimaginably dense state and had been expanding ever since. These two men, the quiet American observer and the Belgian priest-physicist, had laid the groundwork for a revolution in cosmology, though the revolution itself would not be fully recognized for several more years. For now, in the early and mid-1920s, the whispers of motion were just that, whispers, faint suggestions of a universe in flight, of a cosmos that refused to stand still. The astronomers listened, recorded what they heard, and wondered what it all might mean. The answers would come, in time, but first there was more watching to be done, more photons to be gathered, more spectra to be spread across photographic plates in long, silent exposures under the clear desert skies. High above the city of Pasadena, where the San Gabriel Mountains rise brown and quiet in the California sunlight, there stood in the early 20th century a telescope that would fundamentally alter our understanding of the cosmos. The Hooker telescope, with its mirror spanning 100 inches in diameter, was for a time the largest and most powerful instrument of its kind anywhere in the world, and it sat within a great white dome at the summit of Mount Wilson, waiting patiently for the astronomers who would climb the winding road each evening to peer through its eyepiece at the faint and distant things that populated the night sky. The air at that elevation was thin and steady, and on clear nights the seeing was remarkably good, which meant that the stars resolved themselves into crisp points of light rather than shimmering blurs, and the nebulae, those mysterious cloudy patches scattered across the heavens, revealed details that had never before been glimpsed by human eyes. It was here, in this quiet observatory, perched above the orange groves and the growing sprawl of Los Angeles, that Edwin Hubble would make observations so profound that they would reshape the very framework within which we understand existence itself. Though the work proceeded slowly, methodically, and without any sense of the dramatic upheaval it would eventually cause. To understand what Hubble accomplished, we must first speak of a woman named Henrietta Swan Leavitt, who worked at the Harvard College Observatory in the years before the First World War, and whose patient, meticulous labor laid the foundation for nearly everything that followed. Leavitt was employed as a human computer, which was the term used at the time for the women who performed the tedious but essential work of examining photographic plates, cataloguing stars, and measuring their brightness with painstaking precision. Her particular task involved studying variable stars, which are stars that do not shine with constant intensity, but instead grow brighter and dimmer in regular, repeating cycles, much like a lighthouse whose beam sweeps steadily around and around. She focused her attention on a class of these variables known as Cephids, named after the star Delta Cepheid, which was the first of its kind to be thoroughly documented. What Leavitt discovered, through the examination of thousands upon thousands of these stars in the small Magellanic Cloud, a satellite galaxy visible from the southern hemisphere, was a relationship so elegant and so useful that it would become one of the most important tools in all of astronomy. She noticed that the Cepheid variables followed a pattern, a correlation between how long they took to complete one cycle of brightening and dimming and how luminous they actually were. The stars that pulsed slowly, with periods of 30 or 40 days, were intrinsically very bright indeed, while those that flickered more rapidly, completing their cycles in just a few days, were considerably fainter. This relationship, which Leavitt published in 1912 and which we now call the period luminosity relation, provided something astronomers had long sought: a cosmic yardstick, a way of measuring distances across the vast gulfs of space that separate us from the stars. The principle was beautifully simple. If you could observe a Cepheid variable and measure how long its period was, you would know from Leavitt's relation how bright that star truly was. And if you knew how bright it truly was, you could compare that to how bright it appeared in your telescope. And the difference between those two values would tell you how far away it must be. A candle seen from across a large room appears dimmer than the same candle held close to your face, and by the same logic, stars that are intrinsically brilliant but appear faint must be very far away indeed. Henrietta Leavitt had given astronomers a method for reaching out across the darkness and touching, in a sense, the most distant objects they could see. Edwin Hubble arrived at Mount Wilson in 1919, not long after the end of the war in which he had served, and he brought with him an ambition to settle one of the great astronomical debates of the era, the question of whether the spiral nebulae, those pinwheel-shaped smears of light visible in powerful telescopes, were part of our own Milky Way galaxy, or whether they were separate systems altogether, island universes unto themselves, lying at distances so immense that they strained the imagination. Many astronomers believed the Milky Way constituted the entire cosmos, a single vast collection of stars perhaps a few 100,000 light-years across, with nothing beyond it but empty blackness. Others suspected that the spiral nebulae were far more distant, that they were galaxies in their own right, each containing billions of stars, and that our Milky Way was merely one among countless such assemblages scattered through an almost incomprehensibly large universe. The matter had been debated for years, and it could only be resolved by measurement, by determining the actual distances to these mysterious objects. Hubble focused his attention on the great nebula in the constellation Andromeda, also known as Messier 31 or simply M31, which is visible on clear autumn nights as a faint elongated smudge to the naked eye. Through the Hooker telescope, Andromeda revealed itself in glorious detail, its spiral arms studded with what appeared to be individual stars, and Hubble began the patient work of photographing it night after night, comparing the plates to see if any of those tiny points of light changed in brightness over time. In October of 1923, he found what he had been looking for. On a photographic plate exposed on the 5th of that month, Hubble initially believed he had detected a nova, one of those stellar explosions that briefly flare into brilliance before fading away, and he marked the position with the letter N. But upon comparing this plate with earlier exposures, he realized that the star had not simply appeared and vanished. It had been present all along, growing slowly brighter and then dimmer in a steady, rhythmic pattern. It was not a nova at all. It was a Cepheid variable, one of Henrietta Leavitt's pulsating stars, and Hubble understood immediately what this meant. He crossed out the N on his plate and wrote beside it a single word, followed by an exclamation mark, var, for variable. Using Leavitt's period luminosity relation, Hubble measured the period of this Cepheid, determined its intrinsic brightness, compared that to how faint it appeared in his photographs, and calculated the distance. The answer was astonishing. Andromeda lay at a distance of approximately 900,000 light-years, a figure that placed it far beyond the boundaries of the Milky Way, which at that time was thought to be no more than a few 100,000 light-years in diameter. Later refinements would revise this estimate substantially upward, placing Andromeda at more than 2 million light-years from Earth. But even Hubble's initial measurement was sufficient to demonstrate that the spiral nebulae were not local phenomena, not clouds of gas within our own galaxy, but rather entire galaxies in their own right, separated from us by gulfs of emptiness that the mind struggles to comprehend. The universe, it turned out, was far larger than almost anyone had imagined. But this discovery, remarkable as it was, represented only the beginning of what the Hooker telescope would reveal. To push further into the depths of the cosmos, Hubble needed not only distances but also velocities, measurements of how fast these distant galaxies were moving towards us or away from us. And for this work, he relied upon a collaborator whose life story was as unlikely as any in the history of science, a man named Milton Humason, who had first come to Mount Wilson not as an astronomer but as a mule driver, hauling equipment and supplies up the mountain's rugged trails. Humason had little formal education, having left school after the 8th grade, but he possessed steady hands, remarkable patience, and an intuitive understanding of the great telescope and its peculiarities. He began as a janitor at the observatory, then became a night assistant, and eventually proved himself so skilled at the delicate work of guiding the telescope through long exposures that he was promoted to the position of observer, a role in which he would make contributions of lasting importance. The technique Humason employed to measure velocities was spectroscopy, the analysis of light spread out into its component colors. When light from a distant galaxy passes through a prism or a diffraction grating, it separates into a rainbow of wavelengths, and embedded within this rainbow are dark lines, absorption features caused by atoms in the atmospheres of stars absorbing light at very specific frequencies. These spectral lines serve as fingerprints, identifying the chemical elements present in the source, and their positions within the spectrum are precisely known from laboratory experiments conducted here on Earth. But when Humason examined the spectra of distant galaxies, he noticed something curious. The lines were not quite where they should have been. They had shifted slightly toward the red end of the spectrum, toward longer wavelengths, and this shift, known as redshift, indicated that the galaxies were moving away from us, their light stretched by their recession in the same way that the pitch of a siren drops as an ambulance speeds away down the road. Working together over a period of several years, Hubble and Humason assembled a dataset that would change everything. Hubble determined distances to dozens of galaxies using Cepheid variables and other methods, while Humason measured their velocities from the redshifts of their spectra, enduring long cold nights at the telescope as he gathered the faint light necessary for analysis. The spectra of distant galaxies required exposures that sometimes lasted for many hours, and Humason would sit motionless at the guiding eyepiece, making tiny corrections to keep the telescope precisely aligned as the Earth rotated beneath the stars. The results of this painstaking labor were published by Hubble in 1929, based on observations of 46 galaxies, and they revealed a pattern that no one had anticipated. The more distant a galaxy was, the faster it appeared to be receding from us. Galaxies in the nearby Virgo cluster were moving away at velocities of roughly 1,000 kilometers per second, while more distant objects were receding even faster, their redshifts proportionally greater. There was a linear relationship between distance and velocity, a constant ratio that we now call the Hubble constant. And this relationship implied something truly extraordinary. The universe was not static. It was not a fixed and unchanging backdrop against which the stars wheeled in their courses. The universe itself was expanding, the fabric of space stretching in all directions, carrying the galaxies along with it like raisins embedded in a loaf of bread dough that is rising in a warm oven. The raisins do not move through the dough. They simply rest where they are. But as the dough expands, the distance between any two raisins increases, and raisins that were far apart to begin with end up even farther apart than those that started close together. In the same way, the galaxies are not rushing through space away from some central point. They are more or less stationary within space, but space itself is stretching, and the light traveling across these expanding distances is stretched as well, shifted toward the red as the universe grows larger with every passing moment. It is worth noting, in the calm spirit of this account, that Hubble himself was curiously reluctant to embrace the full implications of his discovery. He was a careful observer, meticulous and precise, and he preferred to describe what he had measured rather than speculate about what it meant. His 1929 paper spoke of an apparent velocity-distance relation, and he remained cautious about interpreting the redshifts as evidence of true physical motion or cosmic expansion. Others, including the Belgian physicist Georges Lemaitre, who had independently arrived at similar conclusions from theoretical considerations, were more willing to draw the dramatic inference that the universe had a history, that it had once been smaller and denser, that it was changing and evolving on the grandest possible scale. But Hubble, for all his revolutionary contributions, never fully committed himself to the expanding universe interpretation, preferring to let the data speak without embellishment. And yet the data did speak, quietly but unmistakably, and what it said transformed our understanding of the cosmos. The universe was not still. It was not eternal and unchanging. It was, in some profound sense, alive, breathing outward in a slow and steady expansion that had been going on for billions of years and would continue for billions more. The telescope on Mount Wilson, built with such care and operated with such patience, had revealed a truth that even the greatest philosophers of antiquity could never have guessed: that the darkness between the stars is not a fixed and empty void, but a living fabric, stretching moment by moment, carrying all things gently outward into whatever lies beyond the edge of everything we know. When we speak of the universe expanding, the mind quite naturally imagines something rushing outward, like fragments from an explosion scattering through some vast and pre-existing emptiness. Galaxies hurtling away from one another into a dark and waiting void. This picture, comfortable as it may seem, is not quite what cosmologists mean when they describe expansion, and the distinction, though subtle, is worth settling into, slowly, for it touches on something rather peculiar about the nature of space itself, and about what we mean, or fail to mean, when we speak of nothing at all. The expansion of the universe is not a matter of galaxies moving through space, traveling from one location to another the way a ship crosses an ocean. Rather, it is space itself that stretches, the fabric of the cosmos, if we may call it that, gently and continuously extending in all directions, so that the distances between objects grow larger, not because they are racing apart, but because the very medium in which they sit is becoming more expansive. Imagine, if you will, two small dots drawn on a sheet of rubber, and now imagine that rubber being slowly and evenly stretched in all directions. The dots do not crawl across the surface. They do not exert any effort to distance themselves from one another, and yet the space between them grows. This is closer to what cosmologists describe, though even this analogy, as we shall see, has its limits and must be held gently, like most analogies in physics. There is a further peculiarity that often troubles those first encountering this idea, which is the question of where, exactly, the expansion is happening from, and where it is headed. We might ask, naturally enough, where is the center of this expansion, and where is the edge, and what lies beyond? The answer, according to standard cosmology, is that there is no center and no edge, at least not in the way we might expect. The expansion is happening everywhere, at every point in space, uniformly and without preference. Every location in the universe, whether here on Earth or in some distant galaxy cluster, would observe the same phenomenon, all other objects receding, moving away, with those farther away appearing to recede more quickly. This is not because we occupy a special position at the center of things, but because there is no center, no privileged vantage point from which the universe unfurls. The expansion is intrinsic to space itself, woven into its structure, and so every observer, wherever they happen to be, sees themselves as the apparent middle of a retreating cosmos, while in truth no such middle exists. This concept was illustrated quite early in the history of modern cosmology through an analogy that remains popular to this day, sometimes called the balloon analogy, which dates back to discussions in the 1930s as physicists and astronomers were first grappling with the implications of Edwin Hubble's observations. Imagine the surface of a balloon, upon which small dots have been drawn with ink. As the balloon inflates, the rubber stretches, and each dot moves away from every other dot. An ant standing on any one of these dots would observe all other dots receding from it, and might conclude that it sits at the center of the expansion. But the ant would be mistaken, for every dot experiences the same phenomenon, and the surface of the balloon has no center, at least not on the surface itself. The center of the balloon, if we insist on finding one, lies within the three-dimensional interior, but the surface, which is a two-dimensional analogy for our three-dimensional space, has no point that can claim priority. In this way, the balloon helps us understand that expansion need not have a center or an edge, even if our intuitions insist otherwise. But now we arrive at a question that lingers, often unspoken, in the background of these discussions. If the universe is expanding, what is it expanding into? This is where language begins to strain and where careful thinking is required, for the question assumes that space must be spreading into something else, some external emptiness that exists beyond the universe, waiting to receive it. In standard cosmological models, however, there is no such external realm. The universe, in this view, is not expanding into anything. Space is not pushing outward into a pre-existing void, for there is no void out there, no stage upon which the universe performs. Space is simply becoming more of itself, increasing in extent without requiring something beyond to accommodate that growth. This is, admittedly, a difficult notion to hold in the mind, for we are creatures accustomed to thinking in terms of containers and contents, inside and outside. And yet, the mathematics of general relativity, which governs our best models of cosmic expansion, does not require or even permit an external space into which the universe expands. The universe, in this framework, is all there is, and its expansion is an internal property, not a journey outward. And so we must now ask what we mean when we speak of nothing at all. This is where cosmology brushes against philosophy, and where one must tread carefully, for nothing is a word with many meanings, and not all of them agree. In everyday speech, nothing tends to mean an absence, an emptiness, a lack of things. A room with nothing in it is a room without furniture or people, though it still contains air and light and space itself. In philosophy, particularly in metaphysics, nothing has sometimes been taken to mean an absolute absence, a state in which there is no space, no time, no properties, no potential, not even the conditions for anything to exist. This is nothing in its starkest form, and it is not at all clear that such a concept is coherent, or that it could ever be meaningfully discussed. For to speak of nothing at all, we must invoke something, even if only the concept itself. Physics, for its part, offers a different kind of nothing, one that is rather more lively than we might expect. The quantum vacuum, as it is called, is not a passive emptiness but a seething, restless state, the lowest energy configuration of quantum fields, and yet it is far from inert. According to quantum mechanics, the vacuum is filled with fleeting fluctuations, transient disturbances in which pairs of particles and antiparticles briefly emerge and then annihilate, borrowing energy for an instant before repaying it and vanishing. These are sometimes called virtual particles, and while they cannot be observed directly in the way ordinary particles can, their effects are measurable and have been confirmed through experiment. One of the clearest demonstrations of this activity comes from the Casimir effect, a phenomenon first predicted in 1948 by the Dutch physicist Hendrik Casimir. He proposed that if two uncharged metallic plates are placed very close together in a vacuum, the fluctuations of the quantum vacuum between them would differ from those outside, resulting in a net force that pushes the plates together. This force arises not from any conventional interaction, but from the geometry of the vacuum fluctuations themselves. For nearly 50 years, the Casimir effect remained a theoretical prediction, difficult to test because the forces involved are extraordinarily small. It was not until 1997 that the physicist Steve Lamoureux, working at the University of Washington, measured the effect with sufficient precision to confirm Casimir's prediction, demonstrating that the quantum vacuum is not merely theoretical but has tangible physical consequences. The nothing of quantum physics, then, is not truly nothing in the philosophical sense, but a kind of minimal something, a substrate buzzing with latent activity. This distinction between physical and philosophical nothing became the subject of considerable debate following the publication of a book in 2012 by the physicist Lawrence Krauss, titled A Universe from Nothing. Krauss argued that the universe could have arisen spontaneously from the quantum vacuum, requiring no divine intervention or external cause, for the vacuum, though empty of matter, possesses the potential for spontaneous creation and could, under the right conditions, give rise to all the matter and energy we observe. This proposal was met with enthusiasm by some and skepticism by others, particularly among philosophers who questioned whether Krauss's nothing was truly nothing at all. The philosopher David Albert, writing in a review of the book, criticized Krauss for conflating the quantum vacuum with genuine nothingness, pointing out that the vacuum is itself a physical state governed by laws, embedded in space-time, and that to call it nothing is to miss the deeper question of why there is something rather than nothing in the first place. Albert's critique reminded readers that physical theories describe the behavior of existing things, and that the question of why existence itself obtains may lie beyond the reach of physics as currently understood. The debate remains unresolved, and perhaps unresolvable, resting as it does on the boundaries between science and philosophy, between what can be measured and what can only be contemplated. At still smaller scales, the notion of nothing becomes stranger still. The physicist John Archibald Wheeler, a figure of considerable creativity and influence in 20th century physics, proposed that at the very tiniest distances, far smaller than any particle or atom, space-time itself might lose its smooth and continuous character. At the Planck scale, roughly 10 to the negative 35th meters, a distance so small that it defies ordinary intuition, Wheeler suggested that space-time might become turbulent and foamy, a churning sea of fluctuations in which the usual notions of distance and geometry cease to apply. This concept, sometimes called space-time foam, remains speculative, for we have no direct means of probing such minute scales, and our current theories may not be adequate to describe what happens there. But Wheeler's idea hints at a deeper truth, that what we call empty space may not be empty at all, but rather the quietest possible expression of an underlying complexity, a calm surface beneath which something far more intricate may be hiding. Now, when we speak of the edge of the observable universe, we must be careful to distinguish between what is observable and what exists. The observable universe is bounded by a horizon, a kind of conceptual surface beyond which light has not had time to reach us since the beginning of cosmic time. This horizon lies roughly 46 billion light-years away in all directions, a vast sphere centered, for each observer, on their own location. The distance may seem puzzling, for the universe is only about 13.8 billion years old, and one might expect that light could have traveled only that many light-years in that time. But the expansion of space means that objects which emitted light long ago have since moved much farther away, and so the radius of the observable universe is considerably larger than the age of the universe might suggest. Beyond this horizon, there may well be more universe, more galaxies and stars and empty space, but we cannot see it, for its light has not yet arrived, and perhaps never will, depending on how the expansion proceeds. This cosmic horizon is not a wall or a boundary in any physical sense. It is not a place where space ends or where matter gives way to void. It is simply the limit of our observation, defined by the finite speed of light and the finite age of the cosmos. What lies beyond may be much the same as what lies within, or it may be different. We cannot say, for we have no means of looking. The nothing beyond the observable universe, if we insist on calling it that, is not an emptiness that exists out there waiting to be discovered. It may simply be more of the same, or it may be something else entirely, or it may not be a thing at all, for in the absence of any possible observation, the question becomes difficult to frame meaningfully. And so we return to the puzzle with which we began. The universe is expanding, but not into anything. Space stretches, but it does not push outward against some external void. The nothing we imagine out there, beyond the galaxies, beyond the stars, beyond the farthest horizon, may not be out there at all, for there may be no out there in the relevant sense. The nothing of physics is not an empty stage, but a complex and restless state, and the nothing of philosophy may be so absolute as to be unimaginable. Between these two kinds of nothing, cosmology makes its home, describing what can be described and quietly acknowledging what cannot. And as you settle into sleep, you may find some comfort in this thought, that the universe, vast as it is, does not require an edge or a center. does not ask for a void to expand into, but simply continues, quietly and without hurry, being what it is, for as long as it is anything at all. For most of the 20th century, cosmologists held a quiet and seemingly reasonable expectation about the fate of the universe's expansion. The logic was simple enough, almost intuitive in the way that certain physical principles tend to be once you have sat with them for a while. If the universe began in an explosive expansion, and if that expansion flung matter outward in all directions, then surely gravity would act as a gentle but persistent brake upon that outward rush. Every galaxy pulling on every other galaxy, every cluster tugging at its neighbors across the vast gulfs of intergalactic space. All of that mutual attraction working together to slow the expansion down, little by little, over billions of years. It was not unlike imagining a ball thrown upward into the air, rising and rising, but gradually losing speed as Earth's gravity pulls it back, until eventually it reaches the top of its arc and begins to fall. The universe, astronomers assumed, was doing something similar on a cosmic scale, though whether it would ever actually stop expanding or merely slow down forever remained an open and rather interesting question. This expectation was not merely a guess or a hopeful assumption. It was grounded in general relativity, in the mathematics that Einstein himself had developed, mathematics that described how mass and energy curve spacetime and how that curvature governs the motion of everything within it. A universe filled with matter should experience a deceleration in its expansion, because the gravitational attraction between all that matter should act to resist the outward flow. The rate of deceleration would depend on how much matter the universe contained, and measuring that deceleration became one of the great observational goals of late 20th century cosmology. If you could determine how quickly the expansion was slowing, you could work backward to understand the total mass of the universe, its geometry, and perhaps even its ultimate fate. Would it expand forever, growing colder and darker with each passing eon? Or would it eventually halt and reverse, collapsing back upon itself in a fiery reversal of the Big Bang? These were the questions that motivated decades of careful observation, and by the 1990s, astronomers believed they finally had the tools to answer them. The key to measuring cosmic deceleration lay in finding objects whose intrinsic brightness was known, objects that could serve as what astronomers call standard candles. If you know how bright something truly is, and you measure how bright it appears from Earth, you can calculate its distance. This is because light dims in a predictable way as it travels across space, spreading out over an ever larger sphere and delivering less and less energy to any given patch of that sphere. A 100-watt bulb seen from 1 meter away appears quite bright, but seen from 100 meters away, it is barely visible. And the relationship between apparent brightness and distance follows a precise mathematical law. The challenge, of course, is finding objects in the distant universe whose true brightness you can trust. Objects that do not vary unpredictably or differ from one another in ways that would confuse your measurements. Type Ia supernovae emerged as the ideal standard candles for this purpose, and their suitability arises from a rather elegant piece of stellar physics. These explosions occur in binary star systems where a white dwarf, the dense and slowly cooling remnant of a star like our sun, orbits in close proximity to a companion star. The white dwarf gradually siphons material from its companion, drawing hydrogen and helium onto its surface and slowly gaining mass over millions or billions of years. This process continues until the white dwarf approaches a critical threshold known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. At this point, the white dwarf can no longer support itself against its own gravity through the quantum mechanical pressure of its electrons, and a runaway thermonuclear reaction ignites, consuming the entire star in a cataclysmic explosion that briefly outshines its entire host galaxy. Because this explosion always occurs at approximately the same mass, it releases approximately the same amount of energy each time, and this uniformity makes Type Ia supernovae remarkably reliable indicators of cosmic distance. When you see one of these explosions in a distant galaxy, you know, with reasonable precision, how bright it truly is. And from its apparent brightness, you can calculate how far away it lies. By the early 1990s, two independent research teams had set themselves the task of using Type Ia supernovae to measure the deceleration of the universe. The Supernova Cosmology Project, based at Lawrence Berkeley National Laboratory and led by Saul Perlmutter, had been refining their techniques since the mid-1980s, developing automated methods for detecting supernovae in distant galaxies and measuring their properties with great care. The High-Z Supernova Search Team, a collaboration centered around Brian Schmidt in Australia and Adam Rees in the United States, had similar goals and had developed their own sophisticated approaches to the problem. Both teams understood that they were engaged in one of the most important observational programs in modern cosmology, and both expected to measure a deceleration, because that was what the physics demanded. The only question, they assumed, was how large that deceleration would be. To measure deceleration, you need to observe supernovae at a range of distances, comparing nearby explosions with those in very distant galaxies. The light from distant supernovae has been traveling toward us for billions of years, and during that time, the universe has been expanding, stretching the wavelengths of that light and shifting it toward the red end of the spectrum. This cosmological redshift tells you how much the universe has expanded since the light was emitted. And by comparing redshift to distance for many supernovae, you can trace the history of cosmic expansion. If the expansion has been slowing down, then distant supernovae should appear slightly brighter than you would expect based on their redshift alone, because the universe was expanding faster in the past and has since been decelerating. If the expansion has been speeding up, then distant supernovae should appear slightly dimmer than expected, because the universe was expanding more slowly in the past and has since been accelerating. The differences are subtle, requiring careful calibration and meticulous attention to potential sources of error, but they are measurable with sufficiently precise observations. Throughout the 1990s, both teams accumulated data, observing supernovae at ever greater distances and carefully correcting for all the factors that might introduce uncertainty into their measurements. They accounted for the dimming caused by dust between galaxies. They refined their understanding of the slight variations that exist among different Type Ia supernovae, and they cross-checked their results using multiple telescopes and independent analysis methods. Among the supernovae they studied was one designated SN 1997 AP, observed at a redshift of 0.83, corresponding to a time when the universe was roughly half its current age. When the teams measured the brightness of this supernova and compared it to what they expected based on its redshift, they found something troubling. The supernova was dimmer than it should have been, noticeably dimmer, and this dimness implied that it was farther away than a decelerating universe would allow. At first, both teams assumed there must be an error somewhere, some subtle systematic effect they had overlooked, or some unusual property of this particular explosion. But as they gathered more data, observing additional distant supernovae and subjecting their results to every test they could devise, the pattern held. Distant supernovae were consistently dimmer than expected, and the conclusion, however startling, became increasingly difficult to avoid. Brian Schmidt later described the experience of analyzing these results as deeply unsettling. The teams had expected to measure deceleration, had designed their entire observational program around the assumption that the universe was slowing down, and instead they were finding the opposite. The data indicated that the expansion of the universe was not slowing at all, but rather speeding up, accelerating in a way that contradicted their most basic expectations. Schmidt said that they had gone looking for deceleration, fully anticipating that gravity would be winning its long tug-of-war against cosmic expansion, and instead they found the universe running away from itself faster and faster with each passing billion years. The result was so unexpected that both teams spent months checking and rechecking their work, searching for any possible flaw in their analysis that might explain away this anomaly. They consulted with colleagues, they revisited their assumptions, they looked for alternative explanations involving unusual dust or evolving supernova properties, and one by one they ruled these alternatives out. In January of 1998, the Supernova Cosmology Project and the High Z Supernova Search Team announced their findings to the wider scientific community, and the response was a mixture of astonishment and cautious acceptance. Here were two independent groups, using different telescopes and different analysis methods, arriving at the same extraordinary conclusion. The universe was not decelerating under the influence of gravity. It was accelerating, pushed outward by some unknown force or energy that acted in opposition to gravitational attraction. This was not a small effect or a marginal detection. The acceleration was clear and unmistakable in the data, and its implications were profound. Everything cosmologists thought they knew about the ultimate fate of the universe had to be reconsidered in light of this discovery. The cause of this acceleration remained, and to a large extent still remains, a mystery. Cosmologists gave it a name, dark energy. But this name is more of a placeholder than an explanation, a label for our ignorance rather than a description of any understood phenomenon. Whatever dark energy is, it behaves very differently from ordinary matter or radiation. While gravity causes matter to attract other matter, pulling things together over cosmic distances, dark energy seems to exert a repulsive influence, pushing space itself to expand faster and faster as time goes on. The effect is not noticeable on small scales, within galaxies, or even within clusters of galaxies, where gravitational attraction still dominates. But on the largest scales, across the vast emptiness between galactic superclusters. Dark energy rules, driving the universe to expand at an ever-increasing rate. When cosmologists added up all the energy in the universe, attempting to account for ordinary matter, dark matter, and dark energy, they found that dark energy comprises approximately 68% of the total. Ordinary matter, the atoms that make up stars and planets and people, constitutes only about 5%. Dark matter, the invisible gravitational scaffolding that shapes galaxies and clusters, accounts for roughly 27%. This means that the dominant component of the universe, the thing that determines its large-scale behavior and ultimate fate, is something we do not understand at all. We can measure its effects. We can incorporate it into our mathematical models of cosmic evolution. But we cannot point to any known particle or field and say, that is dark energy. That is what makes the universe accelerate. It is one of the great unsolved problems of modern physics, a reminder that even our most successful theories leave vast territories unexplored. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Riess for their discovery of the accelerating expansion of the universe. The Nobel Committee recognized that this finding had transformed our understanding of cosmic history and fate, revealing that the universe is not merely expanding, but running away into the darkness faster and faster, with no sign of ever slowing down. The discovery opened new questions, even as it answered old ones, forcing cosmologists to confront the possibility that most of the universe is made of something utterly foreign to our experience. And so the cosmos was not merely drifting outward in the aftermath of its explosive beginning. It was accelerating, gaining speed with each passing epoch, growing emptier and colder as galaxies receded from one another into isolation. The universe, it turned out, was running away faster and faster into silence. In the year 2001, a satellite no larger than a small automobile was carried beyond the pull of the Earth and set gently into an orbit around the Sun. At a point roughly 1.5 million kilometers from our planet, a location where the gravitational forces of the Earth and the Sun find a kind of equilibrium, allowing a spacecraft to remain relatively stationary with respect to both bodies. This satellite was called the Wilkinson Microwave Anisotropy Probe, though most who worked with it came to know it simply as WMAP, pronounced as a single word, spoken softly in the corridors of NASA's Goddard Space Flight Center and in the physics departments of Princeton and Johns Hopkins and Chicago. Its purpose was deceptively simple to state, though extraordinarily difficult to achieve, and that purpose was to listen, with exquisite sensitivity, to the oldest light in the universe, the faint thermal whisper left behind from a time when the cosmos was only 380,000 years old. A time before stars, before galaxies, before any of the structures we now observe had begun to form. This ancient light, the cosmic microwave background radiation, had been discovered decades earlier, in 1965, by Arno Penzias and Robert Wilson, who had initially mistaken it for noise in their equipment, for interference from pigeon droppings on their antenna, before coming to understand that they were detecting the remnant heat of the Big Bang itself. But the instruments of that era, remarkable as they were, could only measure the overall temperature of this radiation, finding it to be approximately 2.7 Kelvin, just a few degrees above absolute zero, uniform in every direction. What WMAP was designed to do was something far more delicate, something that required placing instruments beyond the distorting influence of the Earth's atmosphere and magnetic field, and that was to detect the tiny variations in this temperature, the minuscule fluctuations that represented the seeds from which all cosmic structure would eventually grow. The fluctuations that WMAP sought to measure were extraordinarily small, differences of only about 1 part in 100,000, which is to say that if you imagined the average temperature of the cosmic microwave background as a perfectly still pond, the variations WMAP was attempting to detect would be ripples no higher than a fraction of a millimeter across a body of water spanning many kilometers. To accomplish this, the satellite carried 2 back-to-back telescopes that continuously compared the temperature of the microwave sky in opposite directions, spinning slowly as it orbited, gradually building up a map of the entire celestial sphere over the course of months and years. The data it returned was subtle, quiet, the kind of information that reveals itself only through patient accumulation and careful statistical analysis. And yet within that data lay answers to some of the most fundamental questions human beings have ever asked about the shape and content and fate of the universe. When the WMAP team finally assembled their map of the cosmic microwave background, what they found was a pattern of slightly warmer and slightly cooler regions, painted across the sky in mottled patches of color, typically rendered in images as blue for cooler and red or yellow for warmer, though the actual temperature differences were far too small for any human sense to perceive directly. These patches were not randomly distributed, and their sizes and the relationships between them told a story that cosmologists had been waiting decades to hear. The technical term for the statistical analysis of these patterns is the angular power spectrum, which describes how much variation exists at different angular scales. And when this spectrum was plotted, it revealed a series of peaks, oscillations in the data that corresponded to sound waves that had propagated through the early universe. These are sometimes called the acoustic peaks, and the term is not metaphorical. For in the dense plasma that filled the cosmos before the emission of the cosmic microwave background, before atoms had formed, pressure waves could propagate through the hot gas of photons and particles, much as sound waves propagate through air. Though at scales spanning hundreds of thousands of light years and at speeds approaching significant fractions of the speed of light. When the universe cooled enough for electrons to combine with nuclei and form neutral atoms, the plasma became transparent. The photons were released to travel freely through space, and the sound waves were frozen in place, their pattern imprinted on the cosmic microwave background for billions of years, waiting for instruments sensitive enough to detect them. The position and height of the first acoustic peak, the dominant feature in the angular power spectrum, carries information about the geometry of the universe, about whether space itself is curved in the manner that Einstein's equations permit, either positively curved like the surface of a sphere, or negatively curved like a saddle, or flat in the Euclidean sense, extending infinitely in all directions without any overall curvature. The data from WMAP indicated, with remarkable precision, that the universe is flat, or so very nearly flat that any curvature is too slight to detect with current instruments. This flatness is not a trivial result, for it implies that the total energy density of the universe is very close to a critical value, a balance point that determines the ultimate fate of cosmic expansion, and it confirms predictions made by the theory of cosmic inflation, the hypothesis that the universe underwent a brief period of exponential expansion in its earliest moments. For 9 years, WMAP continued its patient observations, refining its measurements, reducing the uncertainties, building an increasingly precise picture of the cosmos. And then, in 2009, a new satellite was launched, one that would carry this work forward with even greater sensitivity and resolution. This was the Planck satellite, a mission of the European Space Agency, named after the German physicist Max Planck, whose work on black-body radiation at the turn of the 20th century had laid the foundations for quantum mechanics. Planck carried instruments cooled to temperatures just a fraction of a degree above absolute zero, allowing it to detect the cosmic microwave background with unprecedented precision, resolving features in the temperature map that WMAP had only been able to glimpse. The Planck satellite operated until 2013, when its supply of helium coolant was exhausted, and the data it returned has become the foundation upon which modern cosmology rests. From the Planck measurements, scientists were able to determine the composition of the universe with an accuracy previously unimaginable, finding that ordinary matter, the atoms and molecules from which stars and planets and people are made, constitutes only about 4.9% of the total energy content of the cosmos. Dark matter, the mysterious substance that interacts gravitationally but not electromagnetically, that holds galaxies together but cannot be seen or touched, accounts for approximately 26.8%, and the remaining 68.3%, the dominant component of the universe, is dark energy, the unknown force that drives the accelerating expansion of space itself. These numbers, so quietly stated, represent one of the most profound discoveries in the history of science. The realization that everything we can see and touch and analyze in our laboratories makes up less than 5% of what exists, that the universe is mostly composed of substances we cannot directly detect and do not yet understand. And yet, the scientists who derived these figures did not present them with drama or alarm, but rather with the measured tone of researchers reporting careful observations, acknowledging uncertainties, noting the need for further investigation. The press releases were sober, the scientific papers dense with methodology and error analysis, and the work continued, as it always does, one measurement at a time. While the satellites mapped the cosmic microwave background from space, other researchers were examining the distribution of galaxies across the sky, looking for patterns that might confirm and extend what the microwave observations had revealed. The sound waves that produce the acoustic peaks in the cosmic microwave background did not simply vanish when the universe became transparent to light, for they had left their imprint not only on the radiation but also on the distribution of matter, creating regions of slightly higher and slightly lower density that would, over billions of years, evolve into the clusters and filaments and voids that characterize the large-scale structure of the cosmos. These frozen sound waves, spanning scales of roughly 150 megaparsecs, or about 500 million light-years, could in principle be detected by mapping the positions of millions of galaxies and looking for a characteristic excess in the probability of finding two galaxies separated by that distance. This signature is called the baryon acoustic oscillation, and its detection required galaxy surveys of unprecedented scope. The Sloan Digital Sky Survey, based at Apache Point Observatory in the mountains of New Mexico, began systematic observations in 2000, eventually mapping the positions and redshifts of more than 1 million galaxies. The 2-degree field Galaxy Redshift Survey, conducted at the Anglo-Australian Observatory using a telescope near Coonabarabran in New South Wales, measured more than 200,000 galaxies in the southern sky. From these vast catalogues, the acoustic signal emerged, a subtle but statistically significant bump in the correlation function, confirming that the geometry of the universe is indeed flat and providing an independent check on the measurements of cosmic acceleration. The acoustic oscillations serve as a kind of cosmic ruler, a standard length imprinted on the universe that can be measured at different epochs and used to trace the history of expansion. By comparing the apparent size of this ruler at different redshifts, astronomers can determine how the expansion rate has changed over time, and these measurements consistently support the picture that the universe began accelerating roughly 5 billion years ago, driven by dark energy that behaves very much like Einstein's cosmological constant, exerting a constant negative pressure that causes space itself to expand at an ever-increasing rate. On a mountain in northern Chile, at the Cerro Tololo Inter-American Observatory, another great survey was undertaken, this one designed to image hundreds of millions of galaxies and to track the positions of thousands of supernovae. The Dark Energy Survey began operations in 2013, using a specially constructed camera mounted on the 4-meter Blanco telescope, a camera containing 570 megapixels that could capture vast swaths of the southern sky in a single exposure. Over the course of 6 years, the survey imaged approximately 300 million galaxies, measuring their shapes and colors and positions with sufficient precision to detect the subtle distortions caused by gravitational lensing, the bending of light by intervening mass that Einstein had predicted more than a century before. These distortions, known as weak lensing, provide a way to map the distribution of matter in the universe, regardless of whether that matter emits light. And the Dark Energy Survey used this technique to create detailed maps of dark matter, revealing the invisible scaffolding upon which the visible universe is built. The scientists who conducted this work gathered in quiet rooms to analyze their data, wrote papers filled with careful caveats and systematic uncertainties, and slowly, methodically, pieced together a picture of a cosmos in which the darkness is not merely an absence, but a presence, something that can be measured and mapped and studied, even if it cannot yet be explained. And the work continues, for the great surveys of the past have given way to even more ambitious missions of the present and future. In July of 2023, the European Space Agency launched the Euclid satellite, named after the ancient Greek mathematician whose geometry describes the flat space that observations have revealed. Euclid will map the distribution of galaxies over the past 10 billion years of cosmic history, using both optical and infrared cameras to measure shapes and redshifts, looking for the signature of dark energy in the way structures have grown and the way space has expanded. It will observe billions of galaxies across more than 1/3 of the sky, building a three-dimensional map of the universe with unprecedented depth and precision. Later in this decade, the Nancy Grace Roman Space Telescope, named after the astronomer who is often called the mother of the Hubble Space Telescope, will join Euclid in the search for dark energy, carrying a wide-field camera that can survey large areas of the sky while maintaining the exquisite resolution that space-based observatories provide. These missions represent the accumulated effort of thousands of scientists and engineers across dozens of countries, years of planning and construction and testing, all in the service of understanding a darkness that cannot be touched or seen directly, only inferred from the way it shapes the light and matter we can observe. In remote observatories around the world, in control rooms filled with the soft glow of monitors and the quiet hum of cooling systems, researchers continue their patient work, gathering photons that have traveled billions of years to reach their detectors, measuring positions and temperatures and redshifts with ever-increasing precision. They do not claim to understand dark energy, do not pretend to know why the universe is accelerating or what the darkness truly is. But they measure it nonetheless, map its effects, trace its influence on the evolution of cosmic structure. The darkness itself has become something to study, to respect, to approach with the careful humility that science at its best requires. And perhaps there is something fitting in this, that the greatest mystery of our age is being investigated, not with bold declarations or dramatic revelations, but with patient observation, with careful analysis, with the quiet accumulation of evidence over years and decades. The universe expands into what cannot be seen, driven by what cannot be touched, and the scientists who study it do so knowing that understanding may come slowly, if it comes at all, and that the honest acknowledgement of ignorance is itself a form of progress, a clearing of the ground upon which future knowledge might someday be built. And so we arrive at the point in our contemplation where we must acknowledge that science, for all its remarkable successes in describing the universe, does not yet possess a single, certain answer to the question of why space itself is stretching at an ever-increasing rate. What we have instead are several possible explanations, each internally consistent, each capable of matching our observations to varying degrees, and each carrying with it a particular vision of what the universe fundamentally is. These explanations drift through the literature of cosmology like clouds across a wide sky, some more substantial than others, some catching the light of new evidence and seeming for a moment more solid, others fading somewhat as measurements become more precise. And there is something genuinely restful in contemplating them together, not as competing warriors in some intellectual battle, but as the honest attempts of careful minds to make sense of something that remains, for now, genuinely mysterious. The simplest of these explanations, and in many ways the most enduring, is the one that Albert Einstein himself introduced and then famously rejected, only to have it return more than half a century later as perhaps the leading candidate for explaining cosmic acceleration. This is the cosmological constant, represented in his field equations by the Greek letter lambda, a small symbol carrying enormous implications. When Einstein first added this term to his equations in 1917, he did so for reasons that would later prove unnecessary, attempting to construct a static universe that neither expanded nor contracted, a universe that matched the philosophical assumptions of his era, rather than the dynamic cosmos we now know ourselves to inhabit. When Edwin Hubble's observations demonstrated that galaxies were indeed receding from one another, Einstein reportedly considered the cosmological constant his greatest blunder, an unnecessary complication added to solve a problem that did not actually exist. But the universe, it seems, had other plans for lambda. When observations in the late 1990s revealed that the expansion of space was not merely continuing, but accelerating, cosmologists reached back to Einstein's discarded term and found that it fitted the data remarkably well. The cosmological constant, in its modern interpretation, represents something profoundly simple and yet deeply strange. It suggests that empty space itself possesses an inherent energy, a constant density of energy that does not dilute as the universe expands. Unlike matter, which becomes more spread out as the volume of space increases, and unlike radiation, which both spreads out and loses energy as its wavelengths stretch, this vacuum energy remains stubbornly constant in its density. Every new cubic meter of space that comes into existence as the universe expands arrives already filled with precisely the same amount of energy as every other cubic meter, a kind of cosmic rent that space pays for the privilege of existing. This constancy has a curious consequence for the behavior of gravity. Because this energy density remains fixed while volumes increase, its total contribution to the energy budget of the universe grows steadily over time. And because of the particular way that vacuum energy interacts with the fabric of space-time, governed by its equation of state parameter sitting precisely at -1. It produces not attraction, but repulsion, a pressure that pushes space apart rather than drawing it together. The cosmological constant, thus, offers an elegantly simple answer to why the universe is accelerating. Empty space is not truly empty, but is instead suffused with a uniform field of energy that acts as a kind of anti-gravity, gently but relentlessly pushing everything away from everything else. This explanation is economical, requiring only a single additional parameter to be added to our cosmological models, and it matches current observations with considerable precision. The Planck satellite data, along with measurements of distant supernovae and studies of how galaxies cluster together across the cosmos, all point toward a cosmological constant with a specific value, one that causes space to double in size roughly every 10 billion years at current rates. If this explanation proves correct, then the ultimate fate of our universe is one of continued acceleration, with distant galaxies receding ever faster beyond our cosmic horizon. The observable universe gradually emptying itself of everything except the contents of our own local cluster of galaxies, bound together by gravity too tightly for expansion to tear apart. But the cosmological constant is not the only possibility that physicists and cosmologists have considered. There exists a family of alternative explanations, collectively known as quintessence, a name that deliberately echoes the ancient Greek concept of a fifth element beyond Earth: water, air, and fire. This name was applied to these models by the physicist Paul Steinhardt and his collaborators in 1998, around the same time that the accelerating expansion was first being discovered, and it captures something of the speculative yet grounded nature of this theoretical program. Unlike the cosmological constant, which remains forever fixed and unchanging, quintessence models propose that the dark energy driving cosmic acceleration is dynamic, varying over time and perhaps even across space, carried by what physicists call a scalar field that permeates the universe. A scalar field, in this context, is a quantity that has a value at every point in space and time, but no direction associated with it, unlike a vector field such as a magnetic field, which points in some particular direction at each location. The quintessence field slowly evolves, rolling down what theorists call its potential energy landscape, like a marble rolling very, very slowly down an extremely shallow bowl. As it rolls, the energy stored in the field changes, and so too does its effective pressure, its influence on the expansion rate of the universe. This means that the acceleration we observe today might be different from the acceleration that prevailed in the past or that will occur in the future. The universe might be speeding up now, but could potentially slow down again at some distant epoch, or it might continue accelerating, but at a rate that varies in subtle ways that future observations could, in principle, detect. Quintessence models are attractive to some theorists because they potentially connect the phenomenon of dark energy to fundamental physics in ways that a bare cosmological constant does not. A slowly rolling scalar field is reminiscent of the inflaton field, hypothesized to have driven the rapid expansion in the first fraction of a second after the Big Bang, suggesting that perhaps cosmic acceleration is a recurring feature of our universe rather than a one-time event. These models also offer the intriguing possibility that dark energy might eventually decay or change its character entirely, leading to a universe whose distant future differs dramatically from simple cosmological constant scenarios. Current observations, however, cannot yet distinguish clearly between quintessence and a true cosmological constant, as the precision required to measure tiny changes in the dark energy equation of state over cosmic time remains just beyond our current technological reach. Beyond quintessence lies an even more exotic possibility, one that the physicist Robert Caldwell and his colleagues explored in a 2003 paper that has since generated considerable theoretical interest. This is the scenario known as phantom energy, distinguished by an equation of state parameter that falls below -1, crossing what cosmologists call the phantom divide. In such a universe, the density of dark energy would not merely remain constant as space expands, as with the cosmological constant, nor decrease slowly, as in most quintessence models, but would actually increase over time, growing ever denser even as the volume of space grows larger. This leads to an acceleration of acceleration, a runaway expansion that would ultimately affect structures on every scale. Caldwell and his collaborators traced out the implications of phantom energy to what they termed the Big Rip, a hypothetical end state in which the accelerating expansion eventually overwhelms all the forces that hold structures together. First, the largest clusters of galaxies would be torn apart, Their constituent galaxies drifting irrevocably beyond one another's gravitational reach. Then individual galaxies would dissolve, their stars scattering into the expanding void. Eventually, even solar systems would be disrupted, planets torn from their orbits, and in the final moments, atoms themselves would be ripped apart as the expansion rate diverged toward infinity. This scenario remains a mathematical possibility rather than an observed likelihood, and current data slightly favor an equation of state at or above -1 rather than below it. The Big Rip serves more as an illustration of the strange possibilities inherent in the mathematics of general relativity than as a prediction of our certain future. One pathway among many that the universe might take. There exists another category of explanation entirely, one that does not introduce new forms of energy into the cosmos, but instead proposes that our understanding of gravity itself is incomplete. General relativity, for all its remarkable success in describing phenomena from the orbits of planets to the bending of light around massive objects, might not be the final word on how gravity behaves across cosmological distances and timescales. Modified gravity theories attempt to reproduce the observed acceleration without invoking any new substance to cause it, instead suggesting that the equations governing space-time curvature require adjustment when applied to the universe as a whole. One such approach, known as FR gravity, generalizes general relativity by allowing the gravitational action to depend on more complex functions of the Ricci scalar, a mathematical quantity that describes the curvature of space-time. In standard general relativity, this relationship is linear and simple, but FR theories permit additional terms that become significant only at very large scales or very low curvatures, precisely the conditions prevailing in the cosmos at late times. These additional terms can mimic the effects of dark energy, producing acceleration without requiring any actual substance to fill the void. Another modified gravity approach, developed by Giadvali, Gregory Gabadads, and Massimo Porati in 2000, and known as the DGP brain-world model, imagines that our four-dimensional space-time exists as a kind of membrane floating within a higher dimensional bulk space. In this picture, gravity behaves normally at short distances, but begins to leak into the extra dimensions at cosmological scales, weakening its attractive pull and allowing the universe to accelerate. The mathematics of this model are intricate and beautiful in their own way, drawing on ideas from string theory and higher dimensional geometry, and they demonstrate that the cosmic acceleration we observe admits multiple interpretations depending on our assumptions about the fundamental structure of reality. And then there is the multiverse possibility, an idea that emerges naturally from certain versions of inflationary cosmology and that reframes the question of dark energy entirely. The physicist André Linde and others have developed models of eternal inflation in which the inflationary epoch that began our universe did not end uniformly everywhere, but continues to this day in regions forever beyond our observational reach. In this picture, our universe is one bubble in an endless froth of universes, each with potentially different physical constants and properties, each perhaps possessing different values of the cosmological constant. If the multiverse is real, then the particular value of dark energy we observe in our universe might be explained not by any fundamental principle, but by a kind of selection effect. We exist here because here happens to be where conditions permit the formation of galaxies, stars, planets, and ultimately creatures capable of making observations. Other bubbles with higher values of the cosmological constant would expand too rapidly for structure to form, while those with negative values might collapse before complexity could arise. We find ourselves, inevitably, in one of the rare bubbles where things worked out. This anthropic reasoning troubles some physicists, who feel that it abandons the traditional goal of explaining observed values from first principles. But others accept it as perhaps the best explanation available, particularly in light of a genuinely profound puzzle known as the cosmological constant problem. When physicists attempt to calculate the expected energy density of empty space using the principles of quantum field theory, summing up the contributions of all the virtual particles that flicker in and out of existence in the vacuum, they arrive at a number that is spectacularly, almost comically wrong. The predicted value exceeds the observed value by a factor of approximately 10 to the power of 120, a discrepancy so vast that it defies easy comprehension. This is not a small correction that better measurements might resolve, but an enormous chasm between theory and observation, one of the most significant unsolved problems in all of fundamental physics. Some unknown mechanism must be cancelling out almost all of this vacuum energy, leaving behind only the tiny residue that we observe as dark energy. But no one knows what that mechanism might be, and all attempts to derive the observed value from first principles have so far failed. The cosmological constant problem reminds us that our understanding of the quantum vacuum and its gravitational effects remains profoundly incomplete. We have given names to our ignorance, calling it dark energy or the cosmological constant, and we have constructed mathematical frameworks that describe its effects with precision. But the deeper why remains elusive, hidden somewhere in the unknown territory where quantum mechanics and gravity meet. And perhaps this is itself a kind of knowledge worth holding. Science does not always arrive at final answers, and the honest acknowledgement of uncertainty is not a weakness but a strength, a recognition that the universe exceeds our current understanding while remaining open to future discovery. Let us now take the very long view, the kind of perspective that requires us to release our grip on ordinary timescales and allow our thoughts to drift outward across billions upon billions of years, into a future so distant that it becomes almost restful to contemplate, precisely because it lies so far beyond any urgency we might feel in our daily lives. The universe, as we have been gently exploring, is expanding, and this expansion carries with it certain quiet implications for the very distant future. Implications that physicists and cosmologists have considered with the same patient curiosity that characterizes all careful science, and which we might now consider together as a kind of long, slow meditation on what lies ahead for the cosmos as a whole. In approximately 100 billion years from now, give or take a few billion, which at these scales becomes a rather modest margin of uncertainty, the distant galaxies that we can currently observe will have receded beyond what we call the cosmic horizon, which is to say, the boundary beyond which light cannot reach us within the age of the universe, and future astronomers, if there are any, Looking out from whatever worlds might exist at that unimaginably remote time, we'll see a very different night sky than the one we see tonight. The great clusters and superclusters of galaxies that currently populate our observable universe, the vast cosmic web that we have mapped with such care, all of those structures will have been carried away by the expansion of space itself, moving not through space, but with it, as space itself continues its patient stretching, until the light from those distant islands of stars can no longer bridge the growing gulf between us, and they will fade, not with any dramatic disappearance, but gradually, like ships sailing slowly over a horizon that keeps receding, until they are simply no longer there to be seen. The physicist Freeman Dyson, who spent much of his long and contemplative career thinking about the far future of the universe and the ultimate fate of life and intelligence within it, wrote at length about these matters with a kind of serene acceptance that seems appropriate to our purposes here. Dyson considered timescales that stretched not merely to billions of years, but to numbers so large that they require their own notation to express. Timescales across which even the protons that make up ordinary matter might eventually decay, if certain theories prove correct, and across which black holes themselves would slowly evaporate through the quantum mechanical process that Stephen Hawking described. And throughout these meditations, Dyson maintained a tone of measured curiosity rather than despair, suggesting that intelligence, in whatever form it might take, could potentially find ways to persist and to think and to experience meaning, even in a universe that was running down toward its final states, whatever those states might prove to be. His writings on these subjects have a quality of peaceful speculation that seems well suited to the late hours, a willingness to look at the very largest questions without flinching and without dramatizing, simply considering what might be and what it might mean and whether meaning itself could endure. But let us return to a timescale somewhat closer to our own, though still stretching far beyond any human concerns. Approximately 4.5 billion years from now, when something rather significant will begin to happen in our local neighborhood of space, by which we mean the gravitational dance between our own Milky Way galaxy and the large spiral galaxy we call Andromeda, which is currently approaching us at roughly 110 kilometers per second, a speed that sounds quite fast and is indeed quite fast by earthly standards, but which across the 2.5 million light-years that currently separate our two galaxies translates to a journey lasting those billions of years. A slow approach that has been underway since long before our solar system even existed and will continue long after any of us have returned our borrowed atoms to the cosmic inventory. When the Milky Way and Andromeda finally meet, the encounter will not be a collision in the violent sense that the word might suggest, because galaxies, despite containing hundreds of billions of stars, are mostly empty space, and the distances between individual stars are so vast that the probability of any two stars actually striking each other is vanishingly small. Instead, what will occur is better described as a merging, a gravitational intermingling, as the two great spirals pass through each other and around each other over hundreds of millions of years, their shapes distorting and stretching under mutual gravitational influence. Long tidal tails of stars streaming outward, and then falling back, and then separating again, in a complex choreography that computer simulations have modeled with considerable detail. Until eventually, after perhaps 1 billion years of this slow dance, the two galaxies will settle into a single larger structure, an elliptical galaxy that astronomers have sometimes called Milkomeda, or occasionally Milkdromeda, names that have a certain gentle whimsy to them, combining as they do the identities of two island universes into one. This merged galaxy, Milkomeda, will become our local island in a very real sense, because by that time, or not too long afterward, in cosmic terms, the ongoing expansion of the universe will have carried the other galaxies and galaxy clusters beyond our cosmic horizon, and Milkomeda, along with the smaller galaxies gravitationally bound to it in what we call the local group, will find itself increasingly isolated, a single great gathering of stars in what will appear to be an otherwise empty universe. The other galaxies having faded from view not because they have ceased to exist, but because the light they emit can no longer make the journey across the expanding space between us. And any astronomers observing from within Milkomeda at that distant time, if they had no historical records to inform them otherwise, might reasonably conclude that their single galaxy was all there was, the entire universe, a lonely island in an infinite void, with no way of knowing that beyond their horizon lay countless other islands, forever out of reach, forever unknowable. This concept, which appears in the physics literature under various names, but which we might call cosmic loneliness or cosmic isolation, has been discussed by many cosmologists, often with a kind of wistful acknowledgement that our current era, the era in which we can still see distant galaxies and measure the expansion of the universe and piece together the evidence for the Big Bang, is in some sense a special time, an epoch when the universe is old enough to have formed stars and planets and creatures capable of asking questions, but young enough that we can still see the evidence we need to answer some of them. And this realization can carry with it a certain poignancy, but it need not carry sadness. And indeed, there is something rather peaceful about imagining the universe settling into quieter configurations, the expansion continuing its patient work, the distances growing, the light becoming more sparse, not as a tragedy, but simply as the way things unfold, the way rivers flow to the sea, and the way autumn follows summer, a natural progression that requires no grief. The astronomer and writer Carl Sagan, whose voice itself had a quality of gentle wonder that many people found deeply comforting, spoke often about perspective and about the importance of seeing ourselves in cosmic context, and his famous reflection on the pale blue dot, the photograph taken by the Voyager 1 spacecraft in 1990 that showed Earth as a tiny speck of light suspended in a sunbeam against the vast darkness of space, remains one of the most quietly powerful meditations on human significance and insignificance that has ever been offered. Sagan noted that on that tiny dot, everyone we have ever known or heard of, every saint and sinner, every king and peasant, every young couple in love, lived out their lives, and he suggested that this perspective, rather than diminishing us, might help us to treat one another more kindly and to cherish the pale blue world that is, for now at least, our only home. There is nothing anxious in this perspective when it is held gently, nothing that requires us to feel small in a diminishing way, only a kind of quiet recognition that we are part of something very large and very old and very patient, and that our questions are the same questions that the universe has been asking itself through us for as long as there have been minds capable of asking. Astronauts who have seen Earth from space have often reported a shift in perspective that has come to be called the overview effect, a cognitive shift that many describe as profound and lasting, in which the boundaries between nations seem to disappear and the fragility and beauty of our planet become vividly apparent. And many of these astronauts have noted that the experience was not one of fear or loneliness, but rather of connection and of peace. A sense of belonging to something larger and more enduring than any individual life or any individual concern. The darkness of space, which might seem cold or hostile when imagined from below, becomes from their vantage point a kind of embrace, the context within which our small, bright world exists, and the distant stars, scattered across that darkness in numbers beyond counting, become not reminders of isolation, but evidence of participation in something vast and ongoing. And here you are, in this present moment, lying in your bed, your body at rest, your breath moving quietly in and out. And the atoms that make up your body are the very same atoms that were forged in the cores of ancient stars. The carbon in your cells produced by nuclear fusion in the hearts of red giants billions of years ago. The iron in your blood coming from supernova explosions that scattered their heavy elements across space to eventually coalesce into new stars and new planets, and eventually into you, lying here tonight, wondering about the universe, which is to say, the universe wondering about itself, which is what the universe does when it assembles atoms in the particular patterns that produce consciousness. And there is something rather lovely about that if you hold it gently, something restful about recognizing that you are made of star stuff, contemplating stars. As Sagan himself once noted, participating in a tradition of questioning and wondering that stretches back to the first humans who looked up at the night sky and forward to whatever beings might one day look up at the sky of Milky Way, billions of years from now. Even tonight, while you rest here, astronomers are at work at observatories around the world and beyond it, continuing the patient work of observation and measurement that has characterized human curiosity for centuries. On Mauna Kea, the great dormant volcano in Hawaii, whose summit rises above much of the obscuring atmosphere and provides some of the clearest views of the heavens available from Earth's surface, telescopes are collecting light that left distant objects millions or billions of years ago, adding to our understanding of the universe's structure and history. In the Atacama Desert of Chile, where the air is so dry and the skies so clear that it is one of the finest places on Earth for optical and radio astronomy, other instruments are probing the cosmos, mapping galaxies and searching for the faint signals that might tell us more about the universe's earliest moments and its eventual fate. And high above the atmosphere, orbiting telescopes continue their work free from the distortions of Earth's air. The Hubble Space Telescope, having observed for more than 3 decades now, and the James Webb Space Telescope, turning its infrared instruments toward some of the most distant objects ever seen, peering back in time toward the first galaxies that formed after the Big Bang, while other spacecraft measure the cosmic microwave background and detect gravitational waves and map the distribution of dark matter, each adding small pieces to the vast puzzle that we have been slowly assembling for generations, with many generations more to come. These astronomers, working through the night while much of the world sleeps, leaps, are engaged in something that requires a particular kind of patience, a willingness to spend years or even careers pursuing questions that may not be fully answered within their lifetimes. And there is a quiet nobility in this work that seems worth acknowledging as you lie here. A dedication to understanding that expects no immediate reward and accepts uncertainty as a permanent companion. And yet they continue, as humans have always continued, looking up and wondering, measuring and calculating kilinomas, proposing theories and testing them against observation, at peace with not knowing everything while still committed to knowing whatever can be known. The universe, in all its vastness and strangeness and quiet expansion toward whatever distant future awaits it, holds mysteries that may never be fully resolved. Questions about what lies beyond our cosmic horizon and what came before the Big Bang, and whether other universes exist, and what consciousness really is, and why there is something rather than nothing. And perhaps part of wisdom is making peace with the existence of these mysteries, not as frustrations to be overcome, but as invitations to wonder, as spaces in which imagination and curiosity can move freely without demanding resolution. And perhaps tonight, as you settle more deeply into rest, you might allow the remaining mysteries to be simply what they are, held gently like the question of what the universe is expanding into, which is to say, held without grasping and without anxiety, as a companion rather than a problem. Let the silence that follows these words be itself part of the answer, the stillness that contains the question and does not need to resolve it, the darkness behind your closed eyes connected to the darkness between galaxies, which is not truly darkness, but only the space in which light travels and time unfolds, and the universe continues its patient, becoming